So let's discuss differentiation of transform. So far we have discussed a number of properties to finding Laplace transform as well as inverse Laplace transform. We have used the concept of linearity. Laplace transform is a linear operator. Then we discussed the first shifting theorem, the second shifting theorem and the unit step function to find the Laplace transform as well as the inverse Laplace transform. So now we should discuss a couple of more properties, the differentiation of transform. We know that f of s is equal to, by definition, e minus st f of t dt. This is the definition of Laplace transform. And if I am differentiating, call it 1. Let me have this equation 1. Differentiate with respect to s. So on the left I will have f dash s, and on the right minus t e minus st f t dt. This I have on the with respect to s. So minus t is the derivative. So it could be written minus f dash s here, 0 to infinity e minus st t f of t dt. So if I look carefully, I have f of s is the Laplace transform of f of t. Then minus f dash s is a Laplace transform. Then Laplace transform of t f of t. Because this is a function. This is the function whose Laplace transform is minus f dash s. Call it 2. Look at that. Differentiate again equation 2. Differentiate again equation 2 with respect to s. So I'll get f double dash s there, and 0 to infinity. This is minus t, another t, e minus st f t dt. This I have. Equation 2 I am differentiating with respect to s. So this becomes 0 to infinity e minus st t square f of t dt. It means this is Laplace transform t square f of t is equal to f double dash s. Look at that. By definition, this is the function t square f of t, and its Laplace transform is f double dash s. Similarly, I will have Laplace of t cube f of t is equal to minus 1 raised to the power 3 f triple dash s, and Laplace transform of t n f of t, where n is an integer. So minus 1 raised to the power n, nth derivative of the Laplace transform of the function. Find the Laplace transform of the function and differentiate n time, where minus 1 raised to the power n is with plus or minus sign. You can have. Example. So this formula is used to find Laplace transform as well as Laplace transform inverse. So find the following Laplace transform. T sin t, t e minus t cos t, t square sin hyperbolic t, etc. etc. So couple of functions I have written, and we have to find Laplace transform of those functions by using the property. Let me have a polynomial p. So look, p f of t is minus f dash s. Let me do this. Solution. Let g of t, let me name t e minus t cos t, a function gt I am naming it. I am leaving the polynomial there and f of t. Let f of t is e minus t cos t. This is f of t. I have not taken the polynomial because this is t is as it is. The rest of the function I name it f of t. So I have f of s. I will find the Laplace transform of this. I have the Laplace of cos s over s square plus 1. But first shifting theorem state, if s is there, so because of this exponential, you are replacing s by s plus s minus a everywhere. S is replaced by s plus 1 this time. Minus a means s plus 1. So if you are replacing s by s plus 1, we are left with f of s is equal to s plus 1, s plus 1 whole square plus 1. This is the Laplace, which is s plus 1, s square plus 2s plus 1 plus 1, make it 2, and this is f of s. We have chosen f of t, we find the Laplace transform of f of t. Now going back, t is there. If t is there, it means you have to find derivative of the Laplace transform of f of t. Put a negative sign with it. I have f of s. Let me differentiate f dash s, which is s square plus 2s plus 2 whole square. This is s square plus 2s plus 2. I am applying the quotient rule. Derivative of numerator minus numerator derivative of denominator, which is 2s plus 2. Look at that. So I am simplifying this. S square plus 2s plus 2 minus s2s square minus 2s minus 2s minus 2 divided by s square plus 2s plus 2 whole square. It means f dash s is equal to s square minus 2s square is minus s square plus 2s minus 2s goes plus 2 minus 2 goes, and you are left with minus 2s and s square plus 2s plus 2 whole square. Let me have a minus common, s square plus 2s, s square plus 2s plus 2 whole square. So this is going to be f dash s. So minus f dash s is equal to s square plus 2s, s square plus 2s plus 2 whole square. So I have multiplied both sides with minus. This means Laplace transform of t e minus t cos t is equal to s square plus 2s over s square plus 2s plus 2 whole square. This is going to be. So if a polynomial is there, forget about the polynomial for the time being. Rest of the function you name it, any function, and find its Laplace transform. Once you find the Laplace transform this, then since t is there, t power 1, only single degree polynomial, differentiate this once. Derivative by applying the quotient rule. If you have taken the derivative, then multiply the derivative with minus 1. Once you multiply, and we have seen Laplace transform t f of t is minus f dash s. We have found minus f dash s, so this is the Laplace transform. So this is going to be the method. So similarly, sine hyperbolic t, let me have this. So let g of t is equal to t square sine hyperbolic t, and f of t sine hyperbolic t is your f of t. Forget about t square. Do not work with it. Just the other function, you name it as f of t. Find its Laplace, which you remember, which is 1 over s square minus 1. This is the Laplace. Sine hyperbolic at, a over s square minus a square, but a is 1 this time. Now t square means differentiate once and another time differentiate twice. T square means differentiate twice. So if you are taking the derivative, that becomes minus 2s s square minus 1 whole square. Because if you are taking this minus 1 there, applying the power rule, and this is derivative of this. Then again finding the double derivative. If you're finding the double derivative, that will be the Laplace transform of this whole function. Again, let me have the derivative f double dash s. F double dash s, I am applying the quotient rule. S square minus 1 whole 4. This is s square minus 1 whole square. Let me have negative outside. Negative outside. And 2s is the derivative is 2 minus 2s derivative of denominator, which is s square minus 1 into 2s and bracket close. So minus outside 2 s square minus 1 whole square minus 2 to the 4 to the 8 s square minus 1 divided by s square minus 1 whole 4. Now minus is taken, 2 is taken, s square minus 1 is taken. So here I have left s square minus 1 because the square I have taken 1, so 1 is remaining. Minus 4s square. Because s square minus 1 is taken out, 2 is taken out. So 4 is there and s square is there. So this is s square minus 1 whole 4. So this s square goes with 3. So minus 2 over s square minus 1 whole cube. And in between we are left with minus 3s square minus 1, which is f double dashes. F double dashes. This implies Laplace transform of t square sine hyperbolic t. T square sine hyperbolic t is minus, let me multiply this, 6s square plus 2 divided by s square minus 1 whole cube. Because I have multiplied with this minus 2 minus 3 plus 6s square minus 2 minus plus 2. Or you can write down hyperbolic function in terms of exponential, applying the first shifting theorem and getting the function back. You can do this. Finding the inverse Laplace transform. Finding the inverse Laplace transform. So let me have a couple of functions. Natural log 1 plus omega square over s square. This is natural log s square plus 1 over s minus 1. Something like that. So we are finding the Laplace inverse by using the property of differentiation we have just discussed. Laplace transform t f of t is minus f dash s. This is the property we have used. So we are using the same property and we are finding the Laplace inverse of the functions. Let me have question 1. Solution question number 1. F of s can be written natural log s square plus omega square over s square bracket close. Let me apply the property of natural log s square plus omega square minus s square. Again I am applying one of the property, which is the power is in here, 2 natural log s. This is the property of natural log. Ln a b is b ln a. So power is there in the coefficient as like coefficient. So this is f of s. Now we have to differentiate once. Differentiate once. Once. So this is f dash s is equal to 1 over s square plus omega square into 2s. We are taking the derivative with respect to s. Minus 2 natural log 1 over s. So natural log derivative is 1 over s. Let you are taking minus sign with it. So which is 2 by s minus 2s s square plus omega square. I have multiplied with minus. Taking inverse Laplace transform. Taking inverse Laplace transform. So minus Laplace inverse of f dash s is equal to 2 Laplace inverse 1 over s minus 2 Laplace inverse s over s square plus omega square. Here. This is going to be. Now let me have 1 over s is 1, 2 into 1. Laplace transform of 1 is 1 over s. So its inverse is 1 minus 2 cos omega t. And we know that this formula we are finding, that is Tf of t. That is Tf of t is minus Laplace inverse f dash s. Look at that. So this is negative Laplace inverse f dash s t. This implies Tf of t is this, which I have. 2 minus 2 cos omega t. So I have to find the function whose Laplace is this. Whose Laplace is this? I mean, in s, function is given in s. I have to apply this property, differentiate once, I'll get something familiar. If it is not familiar, differentiate twice. If it's still not familiar, you have to differentiate again. Sometime it happens. So dividing both sides with t, this t goes, your f of t is 2 minus 2 cos omega t over t. So this is the required function whose Laplace is this. So it means if you are given something in the form of natural log, it is quite easy. You are using the property of log and differentiate once. If you are differentiating, might be some familiar expressions, familiar transform you know, because you are knowing this is 2 and this is 2 cos omega t. But if it is not familiar, differentiate once more. According to that, it is double derivative and something. When it is double derivative, there is no more negative sign, but it is t square there. So you can have some.